Welcome back. Let us revisit an electric charge. We know from school that all matter, whether it is solids or liquids or gases, all matter is made up of these fundamental units or these very small particles called atoms. Now, the basic structure of an atom is such that it has a nucleus, which comprises of positively charged protons and neutrons which do not have a charge. The nucleus is around the nucleus we have electrons rotating in their shells or orbits. Electrons we know are negatively charged particles. Each electron has an equal amount of charge as a proton, just that the nature of these two charges is different. The protons are positively charged, whereas the electrons are negatively charged. We call a material or a substance neutral if it has an equal number of protons and electrons. A material is negatively charged if the number of electrons is greater than the protons. And of course, it's positively charged if the protons are greater than the electrons. Charge on one electron is equal to 1.6 into 10 raised to power minus 19 coulomb. And we know that the SI unit for measuring charge is coulomb. Flow of electric charges constitute an electric current. More precisely, an electric current is the rate of flow of charge. It has units coulomb per second, which is also called the ampere. Now over here, you see that what we call the conventional current flow goes from the positive of the battery into the negative. The conventional current flow is taken as the movement of positive charges, whereas now we know that it is actually the electrons which are flowing, and the flow of electronic current is opposite to that of the conventional current. So the electronic current flows from the negative of the battery to the positive of the battery. This diagram here on the right also illustrates the same phenomena, that what we conventionally call the current flow, that is going from the positive to the negative, whereas the electrons or the electronic current is actually flowing in a direction opposite to the conventional current. Now that we know what an electric charge is and the flow of these charges constitutes an electric current, we move on to the material which allows the flow of an electric current. Such a material is called a conductor. It is able to sustain or it is able to allow the flowing of an electric current because conductors typically have a lot of free electrons which are able to constitute an electric current. Typical widely known examples of conductors are copper, aluminium, silver, and mostly other metals. Over here on the right, we are able to look at the structure of a copper atom. Copper has an atomic number of 29, meaning that it has 29 electrons in its orbits or in its shells. And there is one valence electron. Valence electron is the electron which is available in the outermost shell or known as the valence shell. So copper, like other metals, has one valence electron which is not very tightly bound to the copper atom, and it is easily able to dissociate from the rest of the copper atom, which provides for this ample amount of free electrons. By free, we mean that these are those electrons which are able to break free from their atomic structure. So this availability of large number of free electrons which were able to easily break free from their atomic structure allows conductors to conduct electricity. For conductors, their conductivity is very high, and of course then on the contrary their resistivity is very low. Moving on, we move to the type of materials which are the complete opposite of conductors. They are insulators. Insulators do not allow electric current to pass through, mainly because they do not have any free electrons to constitute an electric current. Their valence electrons, the valence shells are typically more filled as compared to the valence shells of conductors, and therefore the valence electrons find it hard to break free from the atomic structure. So now, because insulators do not have this availability of free electrons, therefore they do not constitute an electric current. Over here, we see some typical examples of insulators. For instance, the copper wire, which is able to carry the electric current, is insulated with the help of plastic, which prevents, of course, a lot of undesirable accidents from taking place. So the plastic covering the highly conducting copper wire is an insulating material. Then rubber is an insulating material, glass is an insulator, cloth is insulator, wood is an insulator. Exactly opposite to that of conductors, the insulators have very high resistivity, however their conductivity is very low. We now revisit the two concepts of resistivity and conductivity. Resistivity, as the name suggests, is the ability to oppose or resist the flow of electric current. It is designated by the Greek symbol rho, and we know that rho is equal to Ra divided by L, where R is the resistance, L is the length, and A is the cross-sectional area of the material that is being considered. Conductivity, which is a reciprocal of resistivity, is the ability of the material to allow the flow of an electric current. It is designated by Greek letter sigma. And as this last equation over here suggests, conductivity is the reciprocal of resistivity. Now that we have seen the two extremes, the conductors and the insulators, we move on to the third kind of materials, which are possibly the most important kind. They are the semiconductors. Semiconductors are very important and highly useful in electronics and subsequently in electrical engineering because they have electrical properties which are somewhere in the middle between conductors and insulators. Two widely known and important semiconductors are silicon and germanium. The two tables over here list the typical resistivities and conductivities of conductors, semiconductors, and insulators at the temperature of 27 degrees centigrade. Now, if I look at the table which lists the resistivities, I see that copper, which is a very good conductor, has a very low resistivity. Its resistivity is roughly 1.5 into 10 raised to power minus 6 ohms per centimeter. Whereas silicon, which is a semiconductor, has a relatively higher resistivity. Its resistivity is approximately 2 into 10 raised to power 5 ohms per centimeter. Now, rubber, which is an insulator, has a very high resistivity as compared to both conductor and semiconductors. As you can see, that the resistivity of rubber is 10 raised to power 18. Now, the reverse trend could then be seen with conductivities. The conductivity of conductors is very high, followed by semiconductors, and then finally insulators, whose conductivity is very low. Over here, we look at the atomic structure of the two more well-known semiconductor materials, which are silicon and germanium. Silicon has an atomic number of 14, whereas germanium has an atomic number of 32. Despite different atomic numbers, these two semiconductor materials or even other semiconductor materials have one thing in common, and that is 4 valence electrons. So from this, I even take the liberty to comment over here that semiconductors are basically elements from the 4th group of the periodic table. And as I suggested earlier, that the degree of conductivity or the amount of current that a material can sustain is determined by the number of valence electrons. So for conductors, the valence electrons are fewer than 4. For semiconductors, there are 4 valence electrons, and insulators typically have more than 4 valence electrons. Moving on further, this slide also highlights or points to the fact that I told you earlier that semiconductors are basically elements from the 4th group of the periodic table. This slide over here also introduces two new terms, which is intrinsic semiconductors and extrinsic semiconductors. We're going to revisit this in greater detail later. However, over here, this should suffice for you to understand that intrinsic semiconductors refer to pure semiconductors which do not have any impurity. And these are elements from the fourth group of the periodic table. Extrinsic semiconductors are those to which a certain impurity, which could be an element from the third group or an element from the fifth group, have been added to modify its characteristics in a way that would be then suitable to us. So intrinsic semiconductors are pure semiconductors, whereas extrinsic semiconductors have an impurity added to them from either the third or the fifth group of the periodic table. Over here, now we see that our conductors which have a very high conductivity and low resistivity. Well, the reason behind that is that the conduction band and the valence band of the conductors almost overlaps. And the forbidden gap on the energy gap needed by electrons to go from the valence band, which is the outermost shell of the atom, to the conduction band where they're freely available for conducting electricity is very, very small. In fact, the valence band and the conduction band are overlapping, which is why our conductors have a very high conductivity. And then you're also able to see over here that the forbidden energy gap for semiconductors is smaller than this forbidden energy gap for insulators. So an electron inside the valence band of a semiconductor needs much less energy when compared with an atom, or when compared with an electron in the valence band of an insulator, to break free from that valence band and enter the conduction band. So over here, we look at the effect of temperature on the resistivity of a material. The resistivity of a material depends on the temperature. The resistivity rho is equal to rho naught, 1 plus alpha multiplied with T minus T naught, where rho and rho naught are resistivities at temperature T and T naught respectively. Alpha is temperature coefficient of resistivity. Now, the noteworthy thing over here is that alpha, which is temperature coefficient of resistivity, is positive for conductors, whereas it is negative for semiconductors and insulators. This in effect means that the resistivity of conductors increases with an increase in temperature, whereas the resistivity of semiconductors and insulators decreases with an increase in temperature. The reason behind this is that in conductors, when the temperature is increased, the atoms or the ions, they start vibrating with greater energy. This leads to an increase in the number of collisions between the free electrons and the vibrating ions or the vibrating atomic structure. So with an increase in temperature, because there is an increase in collisions, that in fact increases resistivity, which in fact reduces electric current. Whereas in semiconductors and also in insulators, with an increase in temperature, more electrons, more valence electrons are able to break free from their atomic structure and they become available for conduction of electric current. So as more electrons, or I will more correctly call them charge carriers, with an increase in temperature, as more charge carriers become available, that leads to a decrease in resistivity and an increase in electric current. Over here, we look at how the concentration of charge carriers changes in a semiconductor with an increase in temperature. This we established earlier, that in semiconductors, the amount of charge carriers or the concentration of charge carriers increases with an increase in temperature, which in effect reduces their resistivity and increases their conductivity. So over here we see, based on these two formulas, that for silicon, the concentration of charge carriers doubles for every 6 degrees rise in temperature. Whereas for germanium, the concentration of charge carriers doubles for every 10 degrees centigrade rise in temperature. The small subscript I refers to intrinsic. So it is NiHT is basically concentration of charge carriers at a high temperature inside the intrinsic semiconductor. And NiRT refers to concentration of charge carriers at room temperature for an intrinsic semiconductor. And delta T, of course, is the difference in temperature between a certain high temperature and the room temperature, which we are taking as 27 degrees centigrade. Over here on this last slide is the recommended textbook for this course and a recommended reference book. However, please feel free to make use of any available resource, whether that's books, video lectures, articles, to learn on these topics. Just ensure that the material that you're using is authentic. If I quickly summarize what we learned in this video lecture, we saw that there are mainly, of course there are others, but mainly there are three kinds of materials. The two extremes are conductors and insulators. Conductors allowing the flow of an electric current, whereas insulators completely blocking the flow of an electric current. And then there is this in-between, very special, important kind of material which forms the basis of modern day electronics, and that is a semiconductor. A semiconductor has electrical properties that are in between of conductors and insulators. They are mostly elements from the fourth group of the periodic table. Two most widely known semiconductor materials are silicon and germanium. Out of these also, I must already add here that silicon is most widely used and is more important. And why that is, we will find out during the rest of the course. So these are mainly the more widely known silicon and germanium are the two more widely known semiconductor materials. And then lastly, we saw that the temperature coefficient of resistivity in case of semiconductors is negative, meaning that when the temperature is increased, the concentration of charge carriers increases inside semiconductor materials, and that leads to a reduction in resistivity. And this is a behavior which is opposite to what actually happens inside the conductors.